So here's our basic function f of x equals x plus 2 squared minus 3, and we're going to talk about concavity and increasing and decreasing. We're going to look at this and understand how derivatives help us find all that stuff. First of all, this graph, I can really quickly graph it. 2 to the left and 3 down, right? So there's my graph right there, and so it's going to go, I'm just going to roughly sketch it. It's going to open up, so it'll be like that. So where is it increasing and decreasing? I can tell just by the graph. Where is the graph increasing?
-2.
It's increasing from -2 to infinity, and it's decreasing from -infinity to -2, right? And where's it concave up? The entire thing is concave up,
Okay.
right? So it's concave up. It is concave up from -infinity to +infinity. So let's, and I did that just by analyzing the graph. I graph it from my shifting techniques. You remember doing that?
Mm-hmm. Yeah.
And then I know it's a parabola. So now let's take a look at what it looks like when I take the derivative of this. First of all, I could rewrite this equation as x squared plus 4x plus 4 minus 3, so that's plus 1, right? So it's x squared plus 4x plus 1, just because it'll be easier to take the derivatives this way. So that's what that equation is equal to. So with the derivative of this, I'll do this in orange, f prime of x is equal to 2x plus 4. And 2x plus 4, if I set that equal to 0, I get x equals -2, and that's why that point right there, -2, that tells me the points, the critical points, that we then use. If you remember, you would take that -2 and you would say, what's the sign over here? And well, it's over here. If I plug in like -3 here, plug in -3, and this is negative, and I'll write the word negative, and it's positive over here, and this means that it's decreasing. See how the graph's decreasing? This means that it's increasing, which meant this was a minimum point. And we have all that. Well, then we can take the double derivative. I'll do this in purple. No, I already did purple. What colors am I having? Green. The double derivative, f double prime of x, just take the derivative of this, and I just get 2. And that's just a constant function. So I can't set that equal to 0.
Okay.
And that's why there's no change in concavity. It's all, well, notice this is positive, which means it's concave out. Concave up. Okay, so there's the basic idea. Now let's make it a little more complicated. Let's do f of x equals x cubed plus 3x squared plus 1. Actually, no, let's make this a little bit easier to graph. Let's do just a very basic x plus 3 cubed. I don't like to use the same letter. X plus 2 cubed. So what's the graph of that look like?
Cubic.
It's a cubic shifted left 2, right? Let's make it a little bit more complicated so it's wavy. How would I do that? I think if I just add a 4 here, I think it'll make it a little wavy.
Okay.
It'll change it so this is going to shift. No, it's not going to make it wavy. I want to make it have some points so that we see the concavity change. Oh, actually, this will still work, won't it? Still has the concavity is still different. So, sorry. Let me just erase this and go back to my original. Let's just graph this. So it's going to be at -2, and that's the point of inflection, and it's going to go like that. So it's going to be concave down here, we know, and concave up here. So let's go ahead and think through. It's going to be increasing, and we can see what the graph is doing, but now let's use the calculus to determine what the graph does. F prime of x, if I use the chain rule, I bring this down, 3x plus 2 squared, and then I multiply it by the derivative of the inside, which is just 1. So there's the single derivative, and the double derivative is going to be, do the same thing, 6 times x plus 2. There's the double derivative. And you can see what happens. the points of inflection. All of these things, if I set this equal to 0, it's going to be -2, which tells you that -2 is that point that you want to use to determine where it's increasing, decreasing.
Okay.
And -2 also is going to be the solution for this one, which means it's going to tell you where it's going to be concave up and down. So let's do the, sorry, I'm speaking too fast now. Let's go back. Let's do just the single derivative. Let's erase this for now. The single derivative test says to do what?
Plug in points.
Plug in.
On either side of there.
Right. Find out where that equals 0, which is at -2. And this helps us determine where it's increasing and decreasing.
Yeah.
So what is it doing on the entire graph?
It's
increasing the entire graph, isn't it? Is this graph ever decreasing?
no.
No, so what should I get when I plug in a -3?
Positive.
I should get a positive over here somewhere, right? And what's going to happen? No matter what I plug in there, what's it going to be?
Positive.
So it's going to be positive no matter what I plug in there, and that's why it's increasing everywhere.
Okay.
See how that analytical analysis helps us do that?
Yeah.
All right, so that's the single derivative test. Now let's do the double derivative test again. When we do that, we get 6 times x plus 2. Well, now what happens? I do the same thing. -2. When I plug in -3, what am I going to get? Positive or negative?
Positive.
Plug in -3 here.
Negative.
I'm going to get a negative, which means it's concave what?
Down.
And look at that graph. To the left, it's how?
Concave.
It's concave down.
Okay.
And to the right, plug in 0, let's say. What am I going to get?
Positive.
Which means it's what?
Concave up.
Which it is right there.
Okay.
So that's again just breaking down what the whole derivatives and double derivatives and testing for concavity and testing for increasing, decreasing. That's what we're doing. That's what we're doing every time. So always think back, kind of focus on simple examples that you can really understand, you can really grasp, because you know what the graph looks like and you know what concavity means. And then you can go to another more advanced problem and you could use what you just did to figure it out.
Okay.